Well, in today's lecture, what we are going to do is to talk about bulk deformation processes in metalworking operations. Have you heard of this before? Bulk deformation processes. Have you heard anything of those processes listed here, which are four basic bulk deformation processes, including rolling, forging, extrusion, wire and bar drawing? Have you heard anything of these processes, any one of us?
There are, I think, for making slabs and tubes.
Which one? Indeed,
Rolling is for slabs, for steel slabs.
to make them or to use them as raw materials, to reshape them. Okay, yeah, that's correct. What else? We know of these processes: rolling, forging, extrusion, and drawing. Yep. So you've heard of it. And you know it's being used in order to make some parts of the engine, including connecting rod and what else? Crankshafts and that sort of stuff. Yeah, good. Anyway, today we are going to talk about these processes and do a number of problems on the first two methods, which are of common use in production industries. Why are bulk deformation processes important? Why are these processes important, and we need to know about these processes as the one who is familiar with basics of manufacturing? Reason? Bulk deformation processes are those processes which are used in order to significantly change shape and dimension of the materials, mainly metallic materials, when there is significant change of shape, and when production quantity is relatively high, meaning that productivity in these processes is greater than that of machining processes. By the way, in making use of these processes, we do not waste the material. What do we mean by this? We mean that we do change the shape of the material, but we do not remove material from the raw material. And as I said before, material removal processes are not desirable because we are wasting the material which has been produced. By making use of these processes, we bring our initial material to the final shape or near to final shape by just changing the shape of the material without removal of the material. However, sometimes we can make the final product out of it, and sometimes we bring it very close to the final shape and still be required to do a little bit of machining in order to produce desired accuracy, tolerances, and surface finish. If there is any need, it is much less than machining the whole material, the whole product from a raw material without making use of these processes. By the way, the type of the properties that we can achieve when we utilize these processes is often superior to the properties that we can achieve from machine parts. How does this happen? Let's investigate these processes, then we will find out more. Well, what is the raw material to be used in these processes? We do actually take different shapes and geometries of raw materials in order to be processed in bulk deformation processes. Often, initial materials and raw materials come in the form of bars, cylinders, billets, and various shapes and in different shapes and geometries. And the importance, as I said, the importance of these methods is that we can reshape the material without removal of any material from what is given to us. And because we are changing the shape of the material without removal of the material, what happens is that we can alter the properties of the material at the same time. And generally, we can subject different materials to bulk deformation processes when the temperature of the material is at room temperature, which is called cold forming, or when the temperature of the material is elevated. And we know that when the temperature of the material is elevated, what happens to the material then? It's easier for us to change the shape of the material. Reason, there is a need for less force in order to change the shape of the material when it is at elevated temperature. Generally, we do call a material when it is elevated to a temperature above recrystallization temperature, we call it hot working. Do we know anything about recrystallization temperature? That's something that we had in Materials and Manufacturing 1. What temperature is called recrystallization temperature? A temperature at which new grains of the material are formed. New grains are nucleated and they grow at that elevated temperature. Meaning, why is it called recrystallization? Because new grains are nucleated and they grow, which is called recrystallization process. And as a consequence, when temperature is above recrystallization temperature for a given material, then the magnitude of the change of shape could be much more than cold working processes. And what's the general definition for the range of recrystallization temperatures for a given material? What temperature is called recrystallization temperature? Any temperature which is approximately above 50% of its melting point is called recrystallization temperature. So for example, for pure iron, melting point is 1539, roughly say 1500. Recrystallization temperature would be about 750, 760. 770 indeed would be recrystallization temperature for pure iron, which is at least 50% of its melting point. If the process is taking place at a temperature below recrystallization temperature, it's called cold working. Even if temperature is above room temperature, say for example for pure iron, if it is being processed at a temperature of say 400, 500 degrees C, which is well above room temperature, this is not considered as hot working. This is still considered as cold working. However, we know that even if temperature is elevated to a temperature which is above the temperature of room, it still helps in order to increase the magnitude of the cold working. And it makes it easier for us to change the shape and geometry of the given material. Still helps. But as new grains are not nucleated and formed, it puts a limit on the magnitude of the cold work which can be applied on the material. And what is the positive role that recrystallization plays in metalworking processes? What's the use of nucleation and growth of the grains? What's the use of that in metalworking processes? Well, stress which is present in the material is relieved. I mean, When new grains are nucleated and they grow, a stress-free grain is produced. A stress-free grain is produced which has got the properties of the original material, which is not yet subjected to any deformation. And we change the shape again. And after some time, again, new grains are formed, so we can continue and continue and continue say processing of the material without failure. If this happens at a temperature below recrystallization temperature, then what happens? Material fails once it's been subjected to a stress which is above its yield strength or UTS indeed, ultimate tensile strength. It eventually fails. But if the same process actually is performed at a temperature which is above recrystallization temperature, we can still continue the task as long as it is still above that given temperature without failure. So that's why recrystallization temperature is important. Well, let's begin with rolling. I assume every one of us know what rolling is, right? Every one of us. When a sheet of the material or a slab is being rolled by making use of two opposing rolls, just like that, as we can see here. When do we make use of this process? When we want to reduce the thickness of the given material. As we can see here, there is a slab or a sheet of material which is used as the raw material, and it is being squeezed between the opposing rolls. When it is coming out of the process, the thickness of the material is reduced. However, the volume of the material doesn't change. The volume of the material remains the same. So when thickness reduces and there is no change of volume, what happens? There is an increase in other dimensions, which is width and also length of the material. That's not all. We do also change the properties of the material as well. We haven't just changed the thickness of the material. If it is being performed at room temperature, we are also altering its properties. We know that when a material is subjected to cold working, there is a change of properties, right? This is what we already know. What makes that happen? At room temperature, if rolling is performed, just like the one that we've got on the screen in this picture, if this process is taking place at room temperature, what are the differences of in terms of the properties of the initial material and the material which has been subjected to rolling? Which one is stronger? The raw material or the one which is rolled? Which one? Which one? The first one, you mean the raw material, is stronger and harder. Is it? Or the opposite? It's opposite. The one which is rolled is harder and stronger. And what explains this? Because material has been subjected to cold working. When a material is subjected to cold working, normally it becomes harder and stronger. Reason, it's been deformed. And when a material is deformed, it means that there are always a number of dislocations present in engineering materials. Temperature always plays a role in what we get. It always plays a role in what we achieve. However, we are talking about processing the material at room temperature. Okay? At room temperature, what happens when we are subjecting a material to deformation? As I said, always in normal materials, there are a number of dislocations in the crystalline structure. And they are crystalline defects. This is what we already know, right? Okay. When material is being subjected, it gets deformed. What makes that possible? Motion of those dislocations which are already present in the material. When they move, change of shape and geometry becomes possible. And they keep moving as long as they can move until those dislocations are trapped in the crystal structure somewhere which they cannot move any further. If this is the case, material is really hard because there is no possibility for the dislocation to move. So that's the final shape of the material. However, still there are some other dislocations in other places which can still move. So as we're subjecting the material to more and more cold working, a larger number of, say, dislocations are trapped and cannot move any further. As a consequence, material is stronger. You cannot deform it as easy as before because now there are fewer dislocations available which can make the move. And we can continue this until material fails because material cannot be subjected to any further change of shape at a given time. So if it is still subjected to further deformation, material fails. However, if the same process actually is performed at a temperature which is well above recrystallization temperature, then what happens? As I said before, new grains are formed. In the new grains, there are also new dislocations present. So you can still continue the formation and keep going for some time. Okay? I'm not saying it's unlimited because the magnitude of the deformation which is taking place should be proportional to the number and percentage of the dislocations which are present in the material. If the magnitude of the deformation is beyond that, even a material at elevated temperature or above recrystallization temperature may fail. However, we can subject the material to much more deformation at elevated temperature. Anyway, now let's take a look at this slide here. In order to become familiar with terminology of flat rolling process. What is flat rolling called? What process is called flat rolling? When the rolls are producing a flat sheet, like the one that we can see here. Is this always the case? No. In rolling, we can produce different shapes as well. It's not always flat rolling. Sometimes we produce a flat sheet, which is of common use, and sometimes we do produce different shapes, which I have got a number of shapes which can be produced by making use of the rolling process in the next slide. Well, as we can see here, we've got two opposing rolls which are used in the rolling process, and the material is actually pulled into the gap between the two rolls, and what is leaving the actually the two rolls has got a smaller thickness. The initial thickness of the material is called TO and the final thickness TM. And the radius of the roll is actually indicated by capital R, which is the roll radius. And we've got a pressure which is being applied to the material, pressure P. We've got an incoming speed, which is V0, the speed of the sheet when it is moving in, and the speed of the material when it is moving out. And there is another speed, which is the speed of the roll, which is the roll speed VR. And we've got also parameter L, capital L, which defines the contact length of the roll, be that of the sheet metal. And there is a very useful equation down here which relates initial thickness times initial width of the sheet times V0, which is the initial speed of the sheet. And this is equal to TF, WF, and VF. What explains this? What explains this? The speed of VF is greater than speed V0, right? if this is fixed, T0, of course it's fixed, W0 and WF, if these two are equal, meaning that there is no change of width, what happens? T0 is greater than TF, then V0 would be less than VF, right? Because volume of the material doesn't change. The volume of the material does not change. When there is no change of volume, but there is a change of thickness, and there is no change of width, this parameter is the same as that one, okay? If this is the case, we do not allow the material to actually change its width. So if WO is equal to WF, and TO is greater than TF, then how can we relate VO to VF? VF should be greater. That's for sure. Right? So, on the basis of having the same volume of the material, we can write such an equation. Volume is the same. So, when there is less thickness, there is a greater speed. And sometimes we've got a number of rolls being used as a series. A pair of rolls sitting here, followed by another pair and another pair. And the same equation can be used in order to predict the speed of the sheet between every two pair of rolls. And we've got a change of thickness which is referred to as draft, amount of the thickness reduction. And also we've got another ratio which is called reduction by dividing draft if the draft is divided by initial thickness of the material. Then we can compute reduction of the thickness of the material. Well, we will have a number of problems, and in those problems we will be using those equations which I just explained. Here we can see a number of geometries and shapes which are produced by making use of the rolling process. As I said, other than flat sheets, we can also produce different shapes and geometries which are not flat. And here you can see a number of those shapes. And many of these actually shapes are the ones which are used in different places. Like where? Buildings. We make use of I-beams when constructing buildings, right? That one. That one. Rails are used in constructing railroads. And various types of materials and geometries which are used in construction industry, in manufacturing industry, and in various industries can be produced by making use of rolling process. If we are making use of rolling process, for example, for producing this I-beam, no material is wasted. We've got an input material which has got some shape, and the output is that one. Have we wasted any material? We haven't. Now, if we want to produce this same material while making use of a machining process, how much material has to be removed from the initial material in order to make it? A lot. A lot. And we've got to pay for the machine tool, for electricity, for the cutting tool, for the labor who is taking the cut, and do all of this in order to make that part. And after all, what you get will not be as strong as the one that you have produced by making use of the rolling process. As I said, when this material is subjected to rolling, it is often stronger. Even if we make use of hot rolling, which is at elevated temperature, still we get a desired orientation for the grains which are present in the crystal structure of the material. At elevated temperature, we can alter the orientation of the grains which are random in the material. When material is being subjected to hot working, again, still we can alter the orientation of the material, and as a consequence, we can achieve a better set of properties, a stronger material, a more desirable material. So even hot working does improve the properties of the material, even hot working and also cold working. However, in cold working, there is some residual stress left in the material after it is subjected to the cold working. If we want to get rid of it, we can subject the material to annealing process, which is leaving it in the furnace for some time at elevated temperature in order to get rid of the residual stress, which is possible. It does not often happen, but in case we are it's very important for us to produce a material which is which hasn't got any residual stress in it and is stress-free, then we can make use of this process. And here this picture is taken from a factory when they are making sheet metals. As you can see, there is a sheet metal coming in, and from the other end, this is the roll, and from the other end, as you can see, material is leaving the processing station when its thickness has been reduced. And as you can see, material is really hot. It's really hot. When it is really hot, of course, it's easier to change the shape of the material. We've got to pay in order to elevate the temperature, but in many cases, it is worth paying it in order to make doing the task easier. And here we can see a number of methods which are used in order to roll the material in rolling mills. Well, here this method is called two-high rolling mill because two rolls are being used in order to roll the material. This one is called three-high rolling when material is being rolled once and it returns to the other pair of the rolls and it is subjected to rolling again. So it's been rolled twice instead of once. Of course, we can achieve greater change of geometry and shape. That one in C is called four-high rolling mill because four rolls are being used. And as we can see, there are two smaller rolls and two larger rolls are backing those smaller rolls, the smaller rolls are called work rolls, and the other ones are called backing rolls. Similar to this one in D, where we have got multiple backing rolls and only two work rolls, which are smaller in size. And of course, that's the one that I just mentioned. Sometimes we make use of a number of opposing rolls in order to subject the material to even greater change of thickness. Okay? Okay, that was a very brief description of the rolling process. And the rolling process is also sometimes used in order to change the shape of the material, not when the material is in the form of a billet or, say, sheet metal. For example, here in the top figure, as you can see, the material is being subjected to thread rolling, meaning that the initial material is a rotational material. When it is rolled between two dies, it's being rolled just like this, just like that. By doing this, some threads are being produced on the surface of the material without any removal of the material. And this method is often used for mass production of screws and bolts. We buy them a lot, right? We make use of them a lot. You go to Bunnings, you can see different shapes, different sizes of bolts, screws, whatever, right? They are being produced by making use of this method. Reason? The rate of production is really high, much greater than machining. By the way, the quality of the material that you get when it is produced by making use of thread rolling is greater. Reason, the surface which is produced in method is a material which is squeezed, and it is stronger and harder than a material which is cut by a machine tool. And also, there is no waste of material. Any material which is in, the same volume of the material is out. There is change of shape only, without any removal of the material. So we get better set of properties, and also, as I said, the rate of production is really greater than machining. And here, in this one, we've got a ring which has got, we've got a big ring which has got a small diameter. Here we've got the same volume of the material. And the height of the material is the same. What has changed is the thickness of the material and its diameter. What we get is a larger material in diameter and also a superior set of properties. If it is at room temperature, which is cold working, then what you get is a stronger material. If it is at elevated temperature, which is hot working, then what you get has got aligned orientation for the crystal structure, providing us with superior set of properties. And they are both, they both improve the properties of the material. Okay, any questions so far? Let's do a problem to see how we can do the computation of the problems in rolling. This is a simple example. First, let me explain the equation sheet to be used in order to do the problem, this problem. This is the equation sheet which I have uploaded for this lecture. We are familiar with this stress-strain diagram from the past, right? This is very familiar to us, this diagram. We've got true strain versus true stress. The stress being represented on the vertical axis and the strain on the, say, horizontal axis. For this given curve, it's referred to as shear rate, which is also being represented by epsilon, which is often used to represent strain. And now we are talking about change of the shape of the material. If we are a design engineer, we are often interested in this part of the stress-strain curve, in this part, in the linear part, which is the elastic part. We know that, right? What happens in the elastic part? If there is a change of shape, it's not permanent. You withdraw the load, it returns to the original shape and geometry, because it's within the elastic region. As we pass this point, which is the yield strength, within this region, if the magnitude of the stress is beyond this point, then there is a permanent change of shape, right? Meaning that if the material is stretched beyond that point, it returns slightly to original length, but not exactly to the original shape. There is some permanent change of length which stays in place. The same for any other type of change of shape. Now, if you are a manufacturing engineer, which is the subject of this unit, this lecture, we are manufacturing, we are talking about manufacturing. We are more interested in this part of the curve rather than this part, because we want to change the shape of the material. If this is to happen, we've got to focus in this part, which is the plastic deformation region of the curve, beyond this stress, which is yield strength. Okay? So design engineers focus at this point, manufacturing engineers focus at this point. If you are doing both, okay, you've got to take a look at the design region depending on what you are doing. In this lecture, as I said, we are talking about deformation, and deformation takes place in this region, not in this region. In this region, Hooke's law is valid. We know that. How about this region? What represents the behavior of the curve in this region? This simple equation. This simple equation, which is telling us about final flow stress. Final flow stress, YF, which is this. Indeed, the behavior of the material in this region is represented by this simple equation, which I have taken from chapter 6. This is chapter 16. The lecture which I am talking about is explained in chapter 17. However, I have taken these two equations from chapter 16 in order to be able to continue with what is being presented in this lecture. And here we've got yield strength, here we've got final flow stress. What is flowing? It's the material. When we are changing the shape, we want to make the material flow in order to take the new shape. Okay? So that's why it is called flow stress. We've got to achieve the flow stress in order to make the material flow and take the new shape. And we are unsure about what is the right magnitude of the flow stress to be used. As a consequence, a parameter which is referred to as average flow stress, or YF bar, is also defined. Taking into consideration a strain of the material, which is being represented here, and two coefficients, K, which is the strength coefficient of the material, and its magnitude depends on the type of the material. It's different for different materials. And we've got also another exponent up here, exponent N, which is referred to as strain hardening exponent. What is it? Strain hardening exponent. That's what I just said. We've got the raw material, okay? The raw material. Its hardness is something. We subject it to deformation, say for example rolling, and we take something out. This material is now harder than the original material, isn't it? It is. You subject the same material to another deformation process, another rolling pass. Again, it becomes harder and harder and harder, depending on the magnitude of the hole working or deformation. What explains the behavior of the material when it is becoming harder and harder? It's different for different materials. They all become harder, however the magnitude of that is different. And this N is taking care of that. Depending on the type of the material, we've got different N values. For some materials it's greater, for some materials it is lower. For those materials which the change of the hardness is really big, we've got a higher value of N. For those materials which become slightly stronger, it's smaller. So, indeed, N is taking care of the slope of the curve within this region. The slope of the curve within this region. It's a curve, it's not a straight line, but if we do draw tangent straight lines to the curve, the slope of the straight lines can be represented by this parameter. Okay? Moving further down, we've got a number of equations, draft, which is something that we had in the lecture note. And for a given material, there is a maximum value of draft. What's that? There is a maximum limit for reduction of the thickness, which is referred to as maximum draft, D max. And here's a function of the radius of the roll R, the radius of the roll R, and also coefficient of friction, represented by parameter mu. And we've got another equation which we had in the previous slide, so I'm going to skip this one. That one also is the forward slip, which can be computed by making use of the speed of the sheet metal and also the speed of the roll. And we've got a number of more equations up to here, which are rolling equations. We've got through strain. This is something which is familiar to us, right? This top equation. We have seen similar equations in the past, right? In the materials and manufacturing, one unit and maybe some other units as well. So through strain can be represented by making use of this equation. However, TO represents the initial thickness of the material and TL final thickness. And we've got an equation for the force of rolling being defined by this equation, and we are familiar with YF bar. W represents the width of the material, and L is the contact length. That's what we have in this slide. And L can be computed by making use of this equation. We are familiar with all the parameters. And then torque for each row is the half of F times L. Why we have got half here? Because there are two rolls. And half of the torque is being applied to each of the two rolls. And finally, the power which is needed in a rolling operation is being defined by this equation, where N represents the rotational speed of the roll. That's all the equations that we need in order to do the problems of rolling. Okay? Now back to the problem. In the problem, we've got a rolling process. The width of the strip is given, or the sheet metal. The width of the sheet metal is that much. Thickness is given, and we are going to roll it by 2 power rolls. The radius of the roll is given, R. Thickness is to be reduced to 22. From 25 millimeters, thickness is to be reduced to 22 in one pass, not multiple passes. The speed of the roll is also given. K, which is the strength coefficient, is given, and N, which is the strain hardening exponent, is also given. If material is being subjected to hot rolling, meaning that the temperature of the operation is above recrystallization temperature, this N should be equal to 0. This N is telling us how much harder material becomes after it is subjected to deformation. Above recrystallization, material does not become harder, meaning that the slope is 0. So when it's hot working, N is always equal to 0. When it is cold working, it has got a value, non-zero value. So it's telling us something. So if we are provided with a hot working operation and N is not given, it's very obvious that N is 0. That's very obvious. If it has got a value, it means that material is getting harder and harder. So it is below recrystallization temperature. Okay? Anyway, we will have another problem to be done in the next session when we have got hot working. So N is equal to 0 for that one, not for this one. And then the coefficient friction between the rolls is given. What we are after is if the friction is sufficient to permit the rolling operation to be accomplished. We've got to see if it is possible to perform this operation, and if so, we've got to compute the force and torque and horsepower needed. First of all, we've got to see if the friction is sufficient in order to make that happen. Indeed, the rolls do play 2 roles. They pull material into the gap between the 2 rolls. And what makes that possible? Friction between the roll and also the sheet metal. If there is sufficient friction, then rolls can pull the material in the gap between the 2. If there is less friction than required, it does not happen. It does not happen. How can we increase friction? How can we increase friction? By removing material from any lubricant or something which plays the role of a lubrication, or by making the surface of the material rougher, which isn't often needed. So if a material is well lubricated, it plays a negative role in the rolling process because we are lowering the friction. And the other role that rolls play is to reduce the thickness of the material. So they play 2 roles: pulling the material into the gap and also squeezing the material in order to change its thickness. Okay. For part A, determine if the friction is sufficient to permit the rolling operation to be accomplished. How do we do that? How do we do that? By taking a look at the equation. We've got a draft, and we've got a maximum draft, right? We've got a maximum draft. And in the equation for the maximum draft, we've got we've got coefficient of friction, which is mu, this one, this equation. This is the one that's telling us what is the maximum draft or change of thickness. Can we make use of this equation in order to compute it? Yep. So, first we've got to compute the draft, which is, for this given case, the difference between the initial and final thickness is 3 millimeters. And by making use of that given equation, which tells us about maximum draft, because coefficient of friction is given and radius of the roll is also given, we can compute maximum draft to be equal to 3.6. If this value is greater than the desired draft, then the process is possible. Then the process is possible. This is greater than that, so this is a feasible process. If this is less than that, then the magnitude of the friction is not enough to accomplish the task. That's what can be concluded. Okay? For this given problem, because this is greater than that, so the magnitude of the friction is sufficient in order to permit the rolling operation. This is a feasible operation.
In manufacturing, how close would you actually have that value to the draft?
Should not be greater than that.
But you could have it the same.
That's maximum value, which is that's it.
And that's what most people do.
Well, no, not really. We often do not roll it to the maximum value. We often don't do that. We do something slightly less than that. What if it is equal is still possible? Okay? The reason is that we've got to see what we want to achieve. What we want to achieve besides what is the magnitude of the deformation. If you want to achieve a thickness of, say, for example, 2 millimeters, then you cannot do it in one pass. This equation is telling you. So you've got to take 2 passes, and you can receive the magnitude of the deformation in 2 passes. Instead of one big pass, one is big deformation, and one slight deformation. It's better to make it something in between. Okay, and next we've got to compute, say, force of rolling, torque of rolling, and horsepower. By making use of those equations that we have got here in the equation sheet, all we need to do is to make use of the right equation. We've got to make use of torque equation, and power equation, and force equation. Do we have all the parameters in order to make use of these equations? If we do it that way. Otherwise, you've got to do the computation of those parameters which are needed. For example, if we want to compute the force required for this rolling process, we need to compute YF bar, which is average flow stress. W is given, L is to be computed. L, which is the contact length, is to be computed. Back to the problem. Okay. So we compute the magnitude of L because all the parameters are given. This is given, this is given, R is also given. Contact length can be computed easily. Okay? This can be computed easily. When this is computed, we've got to move on to compute the magnitude of average flow stress. And in order to do that, K is given, N is also given. However, strain, through strain. We've got the equation. We've got TO and also we've got TF. So we compute epsilon first, which is the true strain, and by substituting all the values which are now at hand, we can easily compute the average flow stress. Having this at hand, it's not hard to compute the magnitude of the required force for rolling. And also, when we have F and L at hand, torque and eventually required power can be computed easily. And please also note that N, which is the rolling speed, is also given in the statement of the problem. By doing this, we have computed all the required parameters which we were supposed to compute in the statement of the problem. What is this 0.5? What role is displayed here? 0.5? Why do we have this here? because we've got two rows. And half of the load is to be applied to each of the rows because the statement of the problem asks us the torque required in each of the rows. And this is the total torque. So we have to divide it by 2 in order to get the torque needed for each of the two rows. Okay. So if operation is hot working, then what do we expect for the value of say strain hardening exponent, and at elevated temperature above recrystallization temperature the value of N would be equal to 0. Reason, at elevated temperature above recrystallization temperature material does not become hardened after deformation. It's always the same, it will always have the same hardness value. Below recrystallization temperature, it gets harder and harder. So there is a value for N which is non-zero. Okay? Good. Any questions so far? If no question, we are going to move on to the next process, which is forging. Maybe it's a good idea to take a break of 10 minutes. Is it? 15? 10 minutes. Okay, starting from now. Well. Let's continue. Let's continue with what is left. It's getting interesting. Forging. Forging is a process which I personally like it very much. I personally like forging very much because it has got a lot of advantages. Regardless of the formation of the material, in order to bring it to the final shape or near to final shape without removing any materials from it. Forging is a process which is widely used in industry in order to produce materials with superior properties. Do we know what forging is? Do we know what forging is? Anyone? We do. What's that then? You said you know what it is. Can you tell us something about it? Just a simple sentence or something. In simple words, whatever you can say. Hammering, yeah. Hammering is a kind of forging operation. And it's been known, forging process has been known to us as human beings since, in this slide it says, since 5000 BC, which is about 7,000 years. But it is even older. There are documents telling us that forging has been known to us for at least 10,000 years. For at least 10,000 years. So this is one of the oldest metalworking processes known to us as human beings, and it's been used in old days in order to make weapons, swords for example. They are the ones which have been used by making use of the forging process. Indeed, I heard from someone that Japanese sword is very famous. I don't know what they call it, katana or something. Have you heard of it, katana? Which is a Japanese sword. It's a well-known sword because it's long, it's sharp, very sharp indeed. And it is very ductile at the same time. It's very ductile at the same time. When you make a material sharp, it must be very hard in order to sharpen it. So if you make a sword which is very sharp, it becomes brittle because it's hard. So when you are fighting with someone with a very sharp sword, it might break because it's fragile. At the same time, you want to have a sharp, which is ductile, which doesn't break when you are fighting with someone, and also you want to make it really sharp. As a consequence, swords made in the past were either sharp or ductile. It wasn't possible to make a ductile and sharp sword, but Japanese made it. Japanese made sharp and ductile swords. How did they do that? Forging. Forging, of course, was used in it, but it wasn't just forging, because the other swords also were forged. They made use of a ductile bar inside another material. The material on the surface was hard, so it was possible for them to make it really sharp. And there was another material inside. It was a two-layered material. The one inside was ductile. So combination of the two did provide them with a composite material, a composite metallic material. What was inside was metal, what was on the surface was also another metallic material. A ductile one and a hard one. Providing them with the material, with the sword which was ductile because of what was in the core of the material, and it was sharp because it was hard on the surface. Is there anyone who has lived in Japan or is Japanese, someone here, Japanese origin? Nobody? Have you ever seen a Japanese sword? Yusuf? He doesn't look like Japanese people, but anyway, I don't know, maybe he has seen it. Yeah, anyway, Japanese have got advanced technologies in so many different areas, including forging and sword making. Anyway, good to know. Good to know. But what I was trying to say is that forging, not swording. Forging is a technology which has been known to us since long time ago. Okay? Now I'm going to play a video clip first before we continue with what is left of the lecture on forging. This is a very interesting video clip, so let's watch this first. Just, I didn't connect the microphone. Let me see where it is. Let's start from beginning.
Forging is the controlled deformation in specific shapes by the use of compressive forces. These forces are applied through tools and dies, driven mainly by hammers, which deform the workpiece at high velocity impact, or presses, which deform the workpiece through controlled high pressures.
Please assume I can't find it.
Processes dating as far back as 8,000
Can you show it to me? Yeah.
It is utilized today to reduce the cross-section, improve the metallurgical microstructure, provide directional grain flow, and eliminate porosity of cast ingot in fabricating rod mill forms, and to form discrete parts to near net shape from these rod mill forms, further refining microstructure and directional grain flow. Because of these effects on microstructure and grain flow, the mechanical performance of rod mill forms and parts is typically superior to that of cast metals. Open die forging is performed on ingot, billet, bar, or a preform, and is the deformation of a workpiece between flat or shaped dies without completely restricting metal flow. This deformation can result in lengthening of the workpiece while reducing its cross-section, upsetting regions along the length to greater sizes than adjacent regions, or even bulging the workpiece's cross-section while reducing its length. Lengthening and upsetting are typically done using multiple impacts as the workpiece is incrementally advanced lengthwise and rotated about its longitudinal axis. There is essentially no limit to the size of forgings forgings that can be made using open die forging. They can range from a few centimeters to 30 meters in length and weigh from a few to up to several 100,000 kilograms. Although fairly complex shapes can be made using open die forging, most are rather simple solids or hollows requiring considerable machining to achieve final shape. Forgings are produced using simple flat, V-shaped, or semi-round dies. Various accessory tools are also used, including saddles, blocks, rings, mandrels, and punches. To withstand forging temperatures, abrasion, and impact, dies and accessory tools are usually made of hot work tool steels or medium carbon alloy steels. Impression die forging, also called closed die forging, is the deformation of metal at forging temperature within one or more die impressions or cavities. It is performed both in presses and hammers. Workpieces may be round or rectangular in cross-section or flat discs, and the dies are sometimes integrally heated to minimize chilling and cooling of the workpiece. For simple shapes, impression die forging can be performed in a single press stroke. More often, however, several strokes of different force are used with dies having several impressions for sequential preforming and finish forging operations. Preforming operations may include edging to increase the workpiece cross-section, blocking to refine the shape for finish forging, and finish forging to complete the shape. In finish forging, the bulk of the metal is forced into the impression, while a thin layer called flash flows out between the dies at the parting plane surrounding the forging. Flash comprises a flat region called the land, and sometimes a bulbous region at the end of the land created by a gutter in the upper die. The thin flash cools rapidly, increasing pressure within the impression, which assists metal flow in the impression details. Once finish forging is complete, the flash is removed either manually or with trimming dies.
Okay,
Quite dangerous.
what was that?
Quite dangerous in the process.
It is, yes, I agree. It's a dangerous process, so we've got to take care of safety issues when we are making use of forging process. Indeed, any manufacturing process to some extent is a dangerous process, but forging and casting and those processes, when we are dealing with elevated temperatures, are more dangerous than other ones, of course. So that's why so many people don't like to work in casting and also forging environments. If they do, they want to get paid more. They expect to get paid more. And they deserve it, of course. Okay? So, in case you work for a forging company, don't worry, you get paid more. Okay. And one of the reasons that I said that I do like this process is that take a look at the typical parts being produced in the forging, by making use of forging process. Crankshafts, connecting rods of the engine, gears, the structural components of the aircraft, and turbine parts and turbine blades. What do we get from these products? Those are all the products which play a significant role, a very important role in what they do, in the product that they are used. For example, the crankshaft is the one which is subjected to what? To extensive forces, and it runs continuously and is being subjected to impact continuously. And it has got to work for years and years just like that. It's not easy for a material to withstand all these impacts at elevated temperature and high speed for a long period of time. They fail after some time because we've got cyclic load being applied as impacts all of the time just like that. The crankshaft rotates in thousands RPMs per minute. And in each rotation, it is being subjected to 2 or 4 impacts, really strong impacts. What material can withstand such a harsh working environment? A material which has been forged. What is this telling us? It has got superior properties. Reason, because it's been forged. Connecting rod plays the same role. Turbine blades, again the same. They work in very actually adverse environment and very difficult to work and withstand situations. So, what can be concluded is that forging does improve the properties of the materials significantly. And that was mentioned in the video clip as well. Okay? And as mentioned in the video clip, we've got 3 common types of forging processes. Forging dies. First of all, let me tell you that forging can also take place at below recrystallization temperature and above, the same as rolling, the same as any other metal forming operation. Again, if it is temperature of the process is below recrystallization temperature, which is 50% of the melting point, then the process is called cold working, even if temperature is well above room temperature. It is still considered as cold working process. If temperature is above recrystallization temperature, then it is called hot working. And in the video clip, we did see that temperature of the material was above melting recrystallization temperature. It was still solid, but it was a soft solid, not a hard solid, which makes it easier for us to deform it. Often, hot working forging operations are used in industry. And we've got 2 different types which are shown in this slide here. We've got open die forging like that one, when we've got 2 flat dies just like that, and we just subject the material to pressure, which could be of the impact type, just like that, or it could be compressive, just subjecting material to compression. Both of them are used and do improve the properties of the material. And that one, which is impression die, then there is a cavity which has got the reverse shape of the desired part. And of course, there is a gap between the 2 halves of the die in order to accommodate the flash, excess material, which is left here. And this flash does play 2 roles indeed. What are the 2 roles that flash plays? If the flash is in here, because there is friction between the surface of the flash and also the surface of the die, it does act as a barrier against the flow of the material. It acts as a brake. So the material cannot flow along this direction and the other direction, and is forced to fill in the cavity of the die instead of flowing. The other role that it plays is that if there is excess material, it does not damage the die and also the machine. The excess material can run into the gap in between, and eventually it will be trimmed of the product which is made.
In this process, we have to make sure you don't produce so much flash, right?
It will be produced. If there is excess material, you don't have to worry about it.
Yeah, but what I mean is that is it necessary to have always a flash?
It will be produced, yes. It's needed. Otherwise, if there is no flash, it's not possible to make a material which does not produce flash. Indeed, in this method, if there is less material, what happens is that the cavity will not be filled, but the flash still will be produced. Because it has to go to this gap in order to act, and there is a minimum surface to be covered in order to apply enough braking force because of the friction. So if there is less than required material, what happens is that you produce incomplete material, incomplete product. There will be some room which is not filled in. And in this very last one, which is the flashless forging, as you can see, there is no flash which is produced. That one is more common than this one. B is more common than C. Reason? If we are making use of method C to produce flashless parts, then what happens is that we don't have trimming to do, which is good, but we've got to be very accurate in computation of the required raw material to fill the gap and to fill the cavity. If there is just a little bit excess material, what happens is that you may damage the doll or the machine. If there is a little bit of less than required material, you produce incomplete parts. So you've got to be exact. There is a need for cross tolerances in order to produce what you want. By the way, this method is often used for making materials which are symmetric in shape and are small in size. For really big ones, you've got to make use of other methods, not this one. As a consequence, this one is more common than that one. That one is also a very common method. In this one, indeed, material is not taking the final shape. What is happening is that we are just improving the properties of the material, but subjecting it to pressure and deformation. We are reorienting the orientation of the grain, of the crystalline structure of the grains. By doing this, we improve the properties of the material. Okay.
Just a question.
Yep.
When the burden properties, the material supply part is being tampered like that, but it's obviously not going to be reused later.
Should be?
It's not going to be reused later.
I am not getting your point.
After it's been tampered, it's going to be tampered while it's put down. It's not going to be heated again, red hot, and then...
Why not? Why not? It could be done several times. It could be repeated again and again until you achieve what you want. The forging process could be repeated again and again because maybe you cannot make this in one go. You've got to do a number of forging steps. So you do it, then you put it away, then you elevate temperature, subject it to another forging process again and again and again, repeated times until you achieve what you want. And as it was mentioned in the video clip, sometimes you cannot bring it to the final shape and geometry because in forging process you cannot achieve close tolerances and high surface finishes. So you may still need to subject it to minor machining operations in order to bring it to the final shape and geometry. However, the magnitude of the amount of the machining required will be significantly reduced because material has taken the initial shape by making use of other processes such as forging. And forging can also take place at lower than recrystallization temperature. If this is the case, still we are improving the properties of the materials. Properties such as strength and also hardness increase when material is squeezed by making use of forging process. Cold forging is also of common use, but of course, hot forging is more common than cold forging. Okay? Does this answer your question? Okay, good. Well, this is a representation of the open die forging process. As you can see, we've got only two flat dies, and what is happening is that we reduce the height of the part which is being forged, but as volume of the material should remain the same, its diameter increases. In this case, which is shown here, we are considering that there is no friction up here between the surfaces of the workpiece and also the die. There is no friction, which isn't the case. There is friction between the two, right? If there is no friction, the change of diameter all the way is the same. If there is friction, this is what you get. This is exaggerated, not that much, but anyway, this is an indication of what happens in practice. There is frictional force between the surfaces of the workpiece and also the die. As a consequence of the frictional force, there is less flow of the material up here compared to this section of the material which is in the middle. Not just that, if forging is taking place at elevated temperature, then there is heat transfer up here, which is more than the heat transfer which takes place in here, meaning that the temperature of the material in the middle will be greater than the temperature of the material up there. When material has got a higher temperature here, deformation in here is easier than the other two ends. So there is more deformation taking place in the middle compared to two ends. Because it's colder on the top and at the bottom. In the middle, it's hotter. This phenomenon is referred to as barreling, because it's taking the shape of a barrel, just like that. Barreling does occur in the forging processes, particularly when forging is taking place at elevated temperature. The magnitude of barreling is much more. Okay. And then, let's skip these ones. Okay, I'm skipping these ones because you can read these ones yourself. Let's move on to a problem on forging. Before we do the problem, let me explain the equations for forging. On top of the equations that we had for rolling, we've got just a few. 3 more equations for forging problems. The top equation is very similar to the one that we had for rolling. However, this time, instead of TO and TF, we have got HO and H representing the height of the material, which is being subjected to forging process. So that's the equation for true strain, and this is the equation required for forging process. In the equation, we've got A, which is the area of the material or cross-sectional area of the material, YF, which is flow stress required to flow the material, and Kf, which is the forging shape factor. What is this shape factor? The shape of the material is not the same. It will be different for different forging parts. And depending on the shape of the material, the magnitude of the required force will be different. Not always we are dealing with a round shaped part. It could have different shapes, square or whatever, any shape. You see in the video clip, we had very different shapes. And depending on the complexity of the shape, the magnitude of the applied force will be different. What takes care of this? Kf. And how do we compute Kf? By making use of this equation down here. And what do we need in order to compute this? Is coefficient of friction, which is right here, and work part diameter. If it is rotational, if it is non-rotational, we've got to put a dimension here, which is representing the size of the average size of the, say, diameter. For example, if it is a square, we've got to take the diagonal of that, 2 diagonals, and get the average size of the two, or depending on different shapes, we've got to compute the right value for D to actually represent the dimension of the part. And H, of course, is the height of the workpiece. Now let's move on to the problem. The problem is representing a cylindrical part. Of course, for cylindrical part, computation of D is easy. It's subjected to a cold offset forging. Offsetting is also another name of forging process. The straight piece is 75 millimeters in height and 50 millimeters in diameter. It is reduced in the operation to a height of 36, and the work material has a flow curve defined by K of that much. N is also given. Where do we make use of K and N? In the flow stress equation that we had for the previous problem. Remember that? Let me go back to the equation sheet again. Up here, these equations, up here, that one. This is an equation for metal forming. It doesn't matter what the operation is. If it is forging, if it is rolling or whatever, this equation is still valid because we are dealing with this curve. And for this curve, in order to represent the behavior of the material in this region, we've got to refer to this, or if we are after the average flow stress, that one. So K and En, which is given in the statement of the problem, can be used here in order to compute the magnitude of YF. These are valid for all the deformation processes. Okay, so K is given, N is also given. N has got a non-zero value. What is this telling us? It's called working operation. I think it was mentioned somewhere as well. Yeah, called offset forging. It's telling us it's not at elevated temperature. So that's why we have got a non-zero N. Assume that a coefficient of friction, which is mu, is given to be 0.1. Determine the force as the process begins at intermediate heights of 62 and 49 and at the end of the process. So we are to compute the magnitude of the required force in the beginning at 2 points in the middle of the operation and eventually at the end of the operation. Do we need different forces at different stages of the operation? Yes, we do. Yes, we do. Okay? Now let's see how we can do this problem. Let's take a look at the equations again. These are the equations for forging. What we are after, not this one, sorry, these ones. What we are after is force, which is represented in this equation. What we need in order to compute that? KF, YF, and A. A cross-sectional area can be computed easily, right? Because diameter is given. It was given. And then YF. How do we compute YF? The equation that I did show you just a minute ago. YF is equal to K times epsilon raised to the power of N. That top equation. Top equation 16.1 can be used in order to compute YF. Once this is done, we compute YF and we need still to compute KF by making use of this equation. When KF is computed from here, YF is computed from the top equation and also A is computed because diameter is given. It's not hard to compute the required force, right? Now, it's telling us in the beginning of the process. Talking about the beginning of the process. In the very beginning, what is height? 75 millimeters. It's given to us. In the statement of the problem. Let's go move back to the problem statement again. It's telling us the height in the beginning is that much, 75 millimeters. And diameter is also given, 50. So, how do we compute the magnitude of YF then? K is given, N is given. We've got to compute the magnitude of strain, true strain. True strain, what's the equation for true strain? That one. How do we do this then? In order to compute YF, we've got to substitute the value of strain. In the very beginning of the operation, we've got to substitute the value of what? The value of yield strengths. Yield strengths, this one. This magnitude. This is the beginning of the formation. Look, in the beginning, the top die touches the top surface of the surface of the die touches the top surface of the workpiece in the very beginning. Just touches that one. And it has to push it down and start the formation. In order to start the formation, the magnitude of the stress has to go beyond this point. Just beyond this point, the formation begins, right? How do we compute the magnitude of Y? How do we compute the magnitude of Y? This is something which I assume you should remember from at least manufacturing 1. You could just get refreshing memory. The magnitude of the strain in the stress strain K. If you remember from materials and manufacturing 1, sometimes we've got a curve like that. When there is no sharp corner differentiating between plastic region and plastic region. In such a case, it's very hard to compute the magnitude of Y. What do? we compute 2% of offset, 2%, 0.002 indeed. And then draw a line wherever this line is parallel to the elastic region, in this region. And whenever there is an intersection between this line and that line, is considered as y. That's the way we do it. Remember that 2% offset? Yeah? Some of us don't. Anyway, if we don't do the magnitude of y, but we've got the curve, we've got to consider a 2% offset. So 2% offset for a strain is a place where it is telling us that it's the beginning of the plastic region. Okay? So if you are after this, you can substitute that much of strain to be sure that it gives us the magnitude of y. If this is the case, if we consider it this way, for a strain, we can substitute the magnitude of 0.002. N is given, K is also given. Then we can compute the magnitude of the required stress in order to begin the formation. Okay? It's 2%. I have to take like that in order to be able to convert it to some equation. 0.2%. 0.2%. Strain, that is a dimensionless unit, unitless dimension. 2% of the total strain. 0.2% of total strain, 0.2% of total strain. No. What we do is that we do draw a line which is offset from the linear region of the strain curve. It's parallel to that one. By 0.2%, it's 0.2%, it's not 2%, 0.2%, okay? Whenever it intersects with the actual curve, the intersection gives us the magnitude of the yield stress. And that's what we need to use in this equation.
Yeah, but I'm just saying how far do you offset it? 0.2%.
Percent of the total
Total strain into a fraction.
The total partial fraction, yes. Okay? So, this is what can be computed then. If we substitute 0 here, for no stress, when there is no strain, no deformation is possible. So we get 0 for the whole equation. But because we are deforming the material, strain cannot be 0. Material has to get elongated before it is deformed. So it cannot be 0. It is something more than 0. And by default, we do consider as 0.2% of the total strain. Didn't we have something like that in the materials and manufacturing one? Maybe we did. Yeah, we did. Anyway, doing it this way, we compute YF for the initiation of the deformation. Having this at hand, we can easily compute the magnitude of KF because diameter is given. And coefficient of friction is also given, height is also given. Everything is given in order to compute KF. So we compute KF. Yep?
I was just wondering, N is 0, meaning that when it's in high operation, high temperature operation, is it okay to say that the coefficient of...
Then you put 0, what you put 0, you get 1 for this. If this is at elevated temperature, this is 0, and this becomes 1. So what you get is 350.
So it's okay to assume that the Y is...
Yeah, if this is at elevated temperature, not elevated temperature, above recrystallization temperature, then N is 0, and you get YF, which is equal to whatever K is. Yeah, that's right. Okay? KF is computed, YF is computed. It's not hard to compute force now, right? Because we've got diameter as well. The required force in the beginning of the operation is that much. Okay? Next. We've got to also compute the required force in intermediate points at a height of 62, 75 we just did it, 62 and 49 and at the end of the process. How do we do this part? For 62, for the height of 62, how do we compute force? Same equations. What do we do? What changes when height changes? When height changes, something changes. What's that? Through strain. Through strain is a function of initial and final height, and that changes. Let's go back to the through strain equation again. The through strain equation for forging, which is down here, that one. We've got initial height, which is 75. We've got current height, which is 62 now. Right? So strain at this height will be different through a strain. So we've got to compute new strain by making use of this equation. And then substitute this equation into YF equation, this value of epsilon. Substitute that one in order to compute a new value for YF. When you've got a new YF, you can substitute new YF here. However, still we need to compute area as well, which is now different. When height changes, when height reduces, area increases. So we've got to work out the new cross-sectional area, right? We've got the same volume, right? Same volume of the material. When height reduces, what happens to diameter? It increases. When diameter increases, area also increases. We've got to substitute the right value for A. So all we need to do is to work out new value for strain, which is that much, new value for KF accordingly, which is that much, and we've got to compute the new value for A according to the change of height. So we can work out, say, B, and then area as well. Where is area computed? Yeah, it's computed right here. That's the area. That's the area because volume is the same. When volume is the same and height changes, you can easily work out area on the basis of that. So this is the new area which is computed, and from here we can compute the new diameter because we've got the area, the only unknown value is diameter. So we can easily compute new diameter. Now we have new D, we've got new A, we've got new YF, and from here we compute new value for KF, and substituting all these into the equation, we need to work out the force at this given stage. We got that? New A, new D, new KF, new YF. Substitute all these in order to compute the amount of required force. Compare this force with the one that we computed in the previous stage. Is it more or less? Is this more or less than the previous force which we computed in the beginning of the operation? Is it more? Let me see. This is what we had. 245 kilonewtons. What we have got here is 650 kilonewtons. It's much more, isn't it? Can we do the same, repeat the same process for the other two heights? When height reduces further and further. Can we make use of the same approach? Work out new strain, new YF, new A, new D, and compute the force again and again for the other two? Similar. Okay? If we do it same way, we compute new forces. At the height of 49, this is the force required. At the height of 36, that much. How does it change then? The required force, how does it change? How can be related to the height of the workpiece? How can we relate required force to the height of the workpiece? As height reduces, required force increases significantly. And if we plot force against height, this is what we get. If we plot required force against change of height, this is what we get. What is this telling us? What is this telling us? In the beginning of the operation, we need minimum force. And as operation or forging process continues, we need more and more force. And it is maximum at the very end of the process. Right? So in the forging process, force begins from minimum and increases significantly and reaches to a maximum at the end of the motion of the, say, die. When it is moving down, at the very end, we need the maximum required force. Okay? I am leaving what is left to you. We've got extrusion and drawing processes. We will have no problems of those two sections. What is left is just reading the process, which I'm leaving it to you. Okay? So the list, extrusion and also drawing, is left to you to cover. Any questions? Okay, thank you very much. We are done with today's lecture and we will have the tutor session